Maybe some students are outside, right? No problem. Well, let's start. Now, today, as a continuation of the previous two lectures, I will go for proving the global convergence of any descent algorithm, first order descent algorithm, when we choose the step length given by the either the exact line search rule or this diminishing step size rule, then they have global convergences. These two particular results are the agenda for today's lecture. At first, I will prove the global convergence for diminishing step size, then I will end up with proving the global convergence under this exact step size rule. Fine. And we are under the two common assumptions. Those assumptions are like f is bounded below. We are minimizing a function. Commonly from the algorithmic viewpoint, we always assume that the function has infimum, it is bounded below. And also we consider that the gradient of f, it is not growing too fast, and by that we here assume that gradient of f is your Lipschitz continuous. Commonly we require in the initial level set that L naught where fx is less than equal to fx naught, but here as this diminishing step size rule does not have always the descensive property, we require this Lipschitz continuity inside the entire domain of the function. Here we are loosely considering the domain as Rn, but here we can replace this as the domain of the function. Fine. Well, so under these two assumptions, next if we consider the step size rule is determined by this diminishing step size, that means we consider now the algorithm that suppose xk is the sequence of iterates given by xk plus 1 is equal to xk plus alpha k dk for every k starting from 0 where dk is a descent direction of f at xk and dk satisfies the angle restriction that I mentioned on the last day, that dk's are uniformly bounded away from the negative gradient which is mathematically this inequality for some c greater than 0, and also we assume that later on maybe here dk we are considering dk is a descent direction, and accumulately this sequence of directions dk we are considering they are bounded above, but this does not lose any generality, because even if I consider dk lies in a compact set, then there is no restriction as such we are taking up, because it is a kind of like a direction can be unitized, it can be normalized, we can think of it is bounded above, because my movement has to happen on this direction, and then the step length alpha k will determine that how much I will move. If I consider my dk to be dk divided by norm dk, the unitized direction, then my alpha length will be just scaled up. So there is no restriction as such if I am taking that norm dk is less than equal to 1 or norm dk is bounded. Fine, that restriction I will require later on. So dk is such a direction that is a descent direction and satisfies the angle restriction, and accumulately all these decays they are lying, the sequence of decays they are lying inside a compact set. Maybe this should not be a point over here, this is a restriction only on for a given decay, and then for every k we have this restriction, and where this happens and the alpha k step length this tends to 0 as k tends to infinity. Then if then we have limit k tends to infinity, norm of, it will be limit infimum, norm of gradient of fxk must be equal to 0. This is what the statement, and in the statement these are common assumptions for any descent algorithm, and then this is also not a kind of condition. Condition is here this angle condition, the diminishing step size rule, and in addition we are considering this decay is bounded above, bounded below certainly norm decay we are considering, and then bounded sequence, and this will conclude that we have the limit infimum of the sequence xk being generated by this iterative formula. We have that value limit infimum is equal to 0. Let us go for proving this result, that why it must happen. We will prove it by the method of contradiction, that if possible, suppose the limit infimum is not equal to 0, then limit infimum k tends to infinity. If it is greater than 0, then then we have norm of fxk is greater than equal to some positive constant mu for all k greater than equal to some integer p, for some p belonging to the natural number set and for some mu greater than 0. Well, we shall see that this will lead to some inequality which will be absurd to hold. Well, so keep it aside. We are assuming that okay, limit infimum is not equal to 0, and then obviously certainly it will be 0 because all the terms are non-negative, and greater than 0 then it will be non-zero, means then greater than 0 over here, and then you have this conclusion, very trivial. But now we note that once we are considering that the function f has gradient leaf siege, then we have the following inequality, that if I construct a function phi of t given by f of xk plus t alpha k dk, we are taking up this function and an auxiliary function it is, then phi dash t is equal to gradient of f xk plus t alpha k dk transpose dk times this alpha k, right? And then we notice that we have phi 1 minus phi 0 is equal to integration 0 to 1 phi dash t dt, and here your phi 1 means what is phi 1? Phi 1 is your f xk plus 1 or f xk plus alpha k dk minus f of xk. This difference is your phi 1 minus phi 0, and then phi dash t is over here, then it will be integration phi dash t means this entire expression, alpha k comes out 0 to 1 gradient of f xk plus t alpha k dk transpose dk td dt, and then we exploit the Lipschitzness of gradient of f. For that we subtract and add the term minus gradient of fxk transpose dk dt, and it will now give us alpha k integration 0 to 1. This portion, this by the Cauchy inequality, this norm and then this norm d less than equal to, right? This portion integrand here is less than equal to norm of grad f this minus grad f xk times norm of dk. Yes. Ah, yeah, yeah, yeah. I subtracted and then added, right? This addition is required. Thankful, sir. Gradient of fxk transpose dk. Fine. Plus alpha k and dt is integration 0 to 1, so on. So alpha k, this will be less than equal to alpha k capital L, this portion norm of the difference, then L times norm of T alpha k dk and norm of dk dt, fine, plus alpha k gradient of fxk transpose dk, right? And then we have this t, the quantity here. Here we are considering this phi function from 0 to infinity to r. That means we are restricting our movement is along the direction dk. Dk is a directed ray, not the entire line, and therefore there is nothing wrong if I am considering here t greater than equal to 0, and then I don't require the analysis for the left hand side, t less than 0. So here then t greater than 0, and then this modulus of t is now simply t, so t square then half, so alpha k square divided by 2, because here t integration, and then you have L over here, you have norm dk square of it, plus alpha k gradient of f xk transpose dk, this term, right? So we have ultimately a neat inequality, and this inequality is not related with the diminishing step size. This entire derivation, you notice that, is for under the general assumption that the function f has gradient Lipschitz. So as long as the function f is Lipschitz, for any alpha k you choose, you have this inequality, that f xk plus 1 is less than equal to f xk plus alpha k gradient fxk transpose dk, plus we have L by 2 alpha k square norm dk square of it, fine. Now we claim that, we notice that alpha k is a diminishing step size, alpha k decreases, alpha k tends to 0, fine, and if alpha k tends to 0, then you notice that alpha k square is then smaller than alpha k, fine, and as alpha k tends to 0, we can somehow sense that this term is going to be ultimately when this term will dominate and this term will be absorbed inside of this, with some tricky inequality obviously, because this alpha k square order small o of alpha k square, and then alpha k square is much smaller, this will be getting absorbed of this one, this term, and ultimately this will be the leading one, fine, and all this perception is now a claim here that we claim, which will be later on useful for proving the result. We claim that we have L by 2 alpha k square norm dk square is less than equal to minus of alpha k, half of alpha k gradient of fxk transpose dk. This term is positive because dk is a descent direction and therefore this term is positive. We should not have any doubt, here is a positive quantity, we may feel like it is less than equal to negative. It is not the fact because dk is a descent direction. Fine, we claim this one and this claim is indeed true. Why? The reason behind it is as follows. This is actually equivalent of the claim that we have norm of dk or like alpha k keep on the left hand side and then push everything on the right hand side. So, this will be less than equal to minus gradient of fxk transpose dk divided by we have L, we have norm of dk square. No term is missed, right? Alpha k. So, this is equivalent of this one. Now, we notice that this is indeed true because alpha k is tending to 0. Why indeed true? I will show that this portion is bounded below by a constant due to our assumption, and alpha k as tending to 0, it is obviously then eventually less than a constant. Alpha k tending to 0 means eventually where after n is larger, this k is larger and larger, then obviously this alpha k will be smaller than any constant you take up. Fine. So, we will show that this portion right hand side is greater than equal to a constant after certain value of k, and that will be sufficient to show that our claim is okay, is not it? And we notice that then to prove our claim, we notice that we have negative gradient transpose dk divided by L norm of dk. This portion is greater than equal to, this is by angle condition, we have greater than c, but on the down we had norm of grad f and xk and norm of dk, right, and divided by, well, so this is square, divided by L norm of dk square of it, right. This gradient of f, what is the raster? So, gradient of f, and then we have here simply this is greater than equal to c by L gradient of fxk divided by norm of dk, okay. And we notice that we started with assuming that limit infimum is greater than 0, then there was a p such that norm of gradient of fxk is greater than equal to mu after the index number p. So, this will be greater than equal to c by L mu after p. So, for all k greater than equal to p, and here norm dk was assumed to be bounded above, and then it has some bound. Let us suppose its bound was norm dk was less than equal to some m for all k due to the boundedness of norm dk, and then 1 by norm dk is greater than equal to capital M. Fine. So, accumulately after the index number p, you have this portion greater than equal to a constant. Fine. And alpha k as tending to 0, So alpha k can be considered as less than equal to C by L times mu by capital M after certain index number, let's suppose P dash. Now you take maximum of P and P dash, then ultimately this claim is true, but this claim is true not for every k, but after certain index number, for all k greater than equal to some P double dash, natural number. Okay. So our claim is validated, and once the claim is validated, then we have the following, that fxk plus 1 less than equal to fxk, this portion I can now have being replaced by, this was less than equal to minus half. So then ultimately this is plus alpha k by 2 gradient fxk transpose dk. Now let us play with this inequality, and we get, let us name that inequality some number 1, say from 1 we now have fxk minus fxk plus 1, that is greater than equal to minus alpha k by 2 gradient of fxk transpose dk. And this inequality happens to be true after certain index number P double dash. And even if we start here, there is no loss of generality. If we start here even from 1, then we have to revise all the sequence xk started from P double dash, because convergence or divergence of a series is always related with like first few terms being deleted, that does not matter, right. In any case, so now if we sum it up here on both the sides, then left hand side is a telescopic sum, fine, and the right hand side ends up with, so here goes with, let us sum it up from k equal to P double dash to some number, let us suppose capital N f xk plus 1, this is greater than equal to minus alpha k by 2 gradient fxk transpose dk, its summation, fine. And notice that this term, if I sum it off, greater than equal to k equal to P double dash to capital N, this term had it been this term, instead of keeping over here, we can even simplify here that this is greater than equal to I want here gradient of fxk transpose dk, means it is less than equal to, this is norm of fxk, norm of dk, right, and then I have this is greater than equal to minus mu, but for dk also we require it is bounded below. if we take up a bounded below, let's suppose small m, so I have this one and then this will be, but with a minus coming out, right? Sir. Sir, coming in, sir.
I think you need here norm of decay bounded above, which you assume, because you have a negative sign.
Yeah, I have a negative sign. So this will be greater than equal to m. Yes. Bounded above, capital M. Am I missing something? Somehow I require here this summation has to be infinity, but here is a finite quantity. If I bring on the left minus alpha k, no mistake. Fxk plus alpha k by 2 L by 2 is
Already because you replace what is underlined minus mu n, and then let capital M go to infinity.
no, so then the inequality will not persist, negative, and then multiply by this quantity. So this inequality will not be greater than, less than equal to, right?
But the negative sign will come with the minus.
Negative.
See the.
Let me check once. Bolo.
Sir, if the negative sign will come with the gradient of f of x k transpose, when the negative is greater than equal to minus norm of
Here,
gradient. So, but here
this.
above you didn't write the minus sign. Minus of gradient of f of x k transpose.
Here you mean?
Yes, here.
But if I take here minus, will this be equal to true? 2.
लेकिन सन 1993 की बात है.
Over here. 2. Done. Thank you. So this will be then greater than equal to, so here goes your, so this minus we keep it over here, and then alpha by 2 here, then minus mu capital M by 2, and then summation k equal to p double dash to capital N, here goes alpha k, right? And then the telescopic sum, will give us f x p double dash minus f x capital N. Fine, this plus 1 is greater than equal to mu m by 2, here this sum k equal to p double dash n alpha k, and this sum goes to infinity, this sum goes to negative infinity as n tends to infinity, or here this part will take later. Here we have f xp double dash is a finite quantity and fxp, and then it has infimum. F has an infimum. F has an infimum means the smallest one. I want somehow this quantity is going to be infinity, but this is a finite quantity. This is finite quantity going to be infinity. How to show this to us? How to show this one?
लेकिन सन 1993 की बात है।
How to show this one? Am I missing some point? Let me check.
There is something I don't understand.
Yes, sir.
Your iteration is will always decrease, am I right?
Iteration? No, no. Decreasing is not assured. Decreasing is not assured. Fxk minus is greater than equal to half of fxk minus, that is okay. And then what did I derive? I derived half of alpha k minus gk transpose. Oh, okay. Yes. In this way, if I simply apply this condition, that Cauchy Schwarz inequality, then not easy. Not easy means then the conclusion that I am wanting, that is not derived. But here what we need to do is that we notice that from here simply I can have the following: this alpha k by 2 negative gradient of fxk transpose dk, this entire part is greater than equal to, this part is greater than equal to alpha k by 2 c times negative gradient fxk norm dk, right? And then this will be greater than equal to alpha k by 2 c times, this is greater than mu, and then we are requiring this dk also bounded below. If I have this portion, then instead of entire this expression, I have capital this mu m and c, mu mc, but we have one additional condition. We are taking up that this dk is not going to be tending to 0. That dk is not only bounded above, but also we are assuming that dk is bounded below, norm dk. That means your direction that you are taking, that is not too small. By too small I mean, if it is tending to be norm dk tending to 0, means it is not almost a direction. And then commonly whenever this Newton direction is converging, has a global convergent and all, those are proven. It is always proven that it is bounded below, and then it was a proven result. So here, in addition to the boundedness condition there, it is not simply boundedness, but on the downside we have not 0 less than equal to norm of dk, we have small mu less than equal to norm of dk, less than equal to capital M. That means in the assumption we take there exists some small m such that we have norm of dk less than equal to capital M for all k. If we take this one, then we have now this which is tending to infinity as n tends to infinity. But here on the left hand side we have this portion, and this portion is always a finite quantity because the infimum is finite, we assumed, and finite quantity greater than infinity, that is not possible. So neatly let me explain here just last few steps where I messed up. Instead of this Cauchy Schwarz inequality, we are employing the angle condition, this angle condition, the angle condition from this underlined portion is greater than equal to c times this portion, right? And once we have this, then this entire expression on the right that I have on this inequality is greater than equal to this condition, this expression, and then as n tends to infinity we have here positive infinity, left hand side cancelling out the telescopic sum, we get a finite quantity and therefore contradictory, right? That this cannot be possible, and then this is due to the initial assumption that the infimum was not 0, and hence the infimum must be equal to 0. This is how the result is proven. Now next we shall prove the result for the exact line search. Exact is little easier, not much trick is there. The result says the following, that let f be bounded below and grad f ellipses continuous on the initial level set L naught given by x belonging to Rn fx less than equal to fx naught. Fine. Common assumption for every first order descent algorithm, and after this we consider the sequence of iterate xk given by the usual rule xk plus 1 is equal to xk plus alpha k dk, but alpha k is now given by exact line search rule. Plus alpha k dk k equal to 0, 1, 2 and so on, where dk satisfies the angle condition angle condition. Consider the sequence for such sequence xk, we have limit k tends to infinity, gradient f xk norm is equal to 0. The reason is as follows. We notice that the function f is such that gradient of f is ellipses. we have already proven at the very beginning of the previous proof that for ellipsis function we have f xk plus alpha k dk. Let us keep alpha as it is instead of there alpha k, although alpha k was not any problem there. For any alpha, any value of alpha you take up, that inequality will be happen to be true. And then f xk plus alpha dk, it will be less than equal to f xk plus you have alpha k into gradient f xk transpose dk plus L by 2 alpha square norm dk. In a similar manner, we can prove the same. Similar manner means the construction of auxiliary function phi t and then phi dash t, and then you take integration from 0 to 1 phi t dt, and ultimately you are going to get this over here. For any value of here alpha, any value you replace, that does not matter. For any value of alpha, this inequality will be happening to be true, and this is a property of a gradient ellipsis function. If the function f is such that its gradient is ellipsis, for that you have this inequality is true. If this inequality is true, we notice that by exact line search rule, the next iterate is taken as fxk plus 1, which is fxk plus alpha k dk. Alpha k is chosen by the exact line search. That means it is nothing but the minimum value over alpha greater than equal to 0 of fxk plus alpha dk. And then in this inequality, I can employ minimum on both the sides, and I get this is less than equal to the minimum most value of this function, but this function is a quadratic function, right? Quadratic function of the variable alpha. We can quickly execute its minimum most value. Its minimum most value, you can just take the derivative with respect to alpha, and we get the derivative value is equal to here we are trying to figure out what is the minimum most value of this expression, and for this expression the minimum most value to figure out, we are taking derivative equal to 0, and then we get gradient fxk transpose dk plus L alpha norm dk is equal to 0. Fine. And then alpha, the minimum would occur at alpha is equal to negative gradient fxk transpose dk divided by L norm dk square. Fine. This is a quadratic function. Here for any given k value, for any particular k, you have this is a constant, this is a constant, this is a positive constant. Fine. So this quadratic function, wheresoever gradient value is equal to 0, we will have the minimum. And but this quadratic function, and this minimum, you notice that is at a positive alpha. Fine. And it is not of the kind that it is getting the value, minimum value at exactly equal to 0. It cannot happen here because of the this quadratic function is such that this constant is over here is positive, this constant here is negative, this gradient of fx transpose dk, and ultimately we are getting here that alpha, and then minimizer is coming over here where alpha is at this particular alpha is strictly positive. This quantity, it is a positive quantity. Fine. And this alpha then plug over here, and we get the minimum most value of this right hand side. Minimum most value is obtained then as fxk plus alpha value we plug, alpha value is this much, and then we have minus gradient fxk transpose dk, that is negative, and then its square divided by L times norm of dk square and plus L by 2 norm of dk square of it alpha square. Alpha square is gradient of f x k transpose dk square of it divided by this dk square will get cancelled and L also will get cancelled over L, then norm of dk square of it, right? And then we simplify it, and the simplification will give us fxk minus half of L gradient fxk transpose dk divided by norm of dk square of it, fine. And this gives us f xk minus f xk plus 1, this is greater than equal to, I have 1 by 2L gradient of fxk transpose dk square of it divided by norm of dk square. And by the angle condition now, I have here this portion inside this square, this portion is greater than equal to c times gradient of norm gradient of fxk square norm of dk square gets cancelled, right? So ultimately this one, right? And then finally I have this result is the simplest most result for the global convergence, that now if we sum it up on both the sides, this now take k equal to 1 to capital N 1 over 2L c square by 2L norm of gradient fxk square of it less than equal to, I have fx1 minus fx, I should have taken starting from 0 even, then I will have here 0 and ending up with fxn, right? And which is a finite quantity. This is a finite quantity. Even if I take capital N tends to infinity, so c square by 2 k equal to 0 to infinity norm of fxk square is less than positive infinity because f is bounded below, and therefore we simply have limit k tends to infinity gradient of fxk transpose is equal to 0, and that is what we wanted to prove. This is the simplest most result. It is simply the application of the Lipschitzness of the gradient. This inequality, like just this inequality is the one which is the gearing force to prove all of the things. The first inequality, and that is the property of a Lipschitz function, Lipschitz gradient, right? So with this the result ends up, and I also stop the lecture here. I planned, yeah. Any query?
Yes, because I am a little bit confused. You consider sometimes that decay, the norm of decay is bounded above, sometimes bounded below. But my question is, the only conditions on decay is that descent directions and satisfy the angle condition.
Yeah, the condition, but in proving the result for the diminishing step size, there we require one additional condition, that norm of decay is bounded, not only just bounded above, but also bounded below by a positive quantity.
But on top, I mean, leaving
Yeah.
aside this non-condition,
Yes.
the only conditions
Yeah.
you use to choose decay is that it is a descent direction
Yes.
and it satisfies the angle
Angle
condition.
condition. Yes.
Then these conditions define a convex A, so there is no loss of generality to assume that the norm of decay is equal to 1, am I right?
Yeah, there is no loss of generality.
Then you can avoid every discussion about the boundedness of the norm of decay. Because it's always equal to 1.
Yes, you are right, but there is a problem. The problem is the following: if I normalize decay, norm of decay equal to 1 I take up, then accordingly the alpha k will get changed. I cannot, yeah, and then I may not have this summation of alpha equal to infinity. Okay, so like if I scale up d, then accordingly alpha k will little bit blow up or like squeeze.
No, that's clear.
Yeah.
So if you assume that the norm of decay is equal to 1 to normalize, what would be the condition on alpha k?
Then for the diminishing step size it will be tricky then, because diminishing step size, the just take that it is summating up is positive infinity and alpha k tends to 0, that may be lost even. If I take simply norm of decay is equal to 1, maybe I can think of a counter example, not right away maybe.
It's a little bit strange to me because then at every iteration, then you choose a direction, but not only a direction. You choose, let's say, the norm of the direction. It's not just saying I'm going this way. You're saying I'm going this way, and the vector I use to represent this direction has this particular norm.
Now, if I commonly here, whenever we take that summation of alpha k tending is positive infinity and alpha k tending to 0, as tending to 0 is there, so alpha k is going to be smaller, is not it? And then if I take decay not very stringently taken as bounded by 1, if I allow it till let's suppose 5, then computationally we have found that alpha k scaling is not required. This alpha k scaling, if I scale up, let's suppose d is very big and I squeeze to 1, and this very big, it is not like blowing up, not norm of decay is going to be infinity. Like very big you take up, accordingly alpha k scaling is not required. And then obviously just if I simply take that instead of norm of decay, not simply less than equal to 1, not unitized, but let's suppose 500. That 500 also, this 500 is so big that it will cover not to scale this alpha k. Practically we have observed, but obviously your query is obviously perfect, that I am always then I am careful not only about decay, I am taking restriction on the would be decay for which the norm of decay is bounded, and that I don't have a control, that which decay I have to choose. And then obviously some pitfall is obviously there. Whenever we are imposing condition, we try to choose conditions which are like as like covering the most general one, but still some restriction is always there when mathematically proving things for a general case. But these are all general cases. We are thinking of any general function we have, not a particular function I have. For a general function, obviously proving global convergence and then sometimes conditions, we need to somehow take something, otherwise the result we may not be able to arrive. Okay? Okay.
है।